I'm going through, yeah, I have a vertical asymptote at x equals 12, but I also have a horizontal asymptote. And so, again, the algebra way to say this would be horizontal asymptote where? Y equals 0, right? And so when I go ahead to sketch a graph, probably the first thing I'll do is I'll draw the asymptotes. So I have a horizontal asymptote here at y equals 0. I have a vertical asymptote at x equals 12. So this is x equals 12. And so now you just kind of want to plot some points, right? And if I graph it on a graphing calculator, it can be deceiving, because if you just do the standard window, it only goes to 10. You won't even see this piece, right? So I have to be smarter than my calculator. I have to know, oh, rational functions have asymptotes. I should look for vertical and horizontal asymptotes. And I'll get a vertical asymptote if I get a non-zero over 0 situation, right? And now, what I want to do is I want to plot some points, right? So for example, I mean, you know, we make an input-output table for graphing, and your calculator does this too, right? You put an x and you put an f of x. I like to throw in a 0. That gives me the y-intercept. So what would be the what would be f of 0 here? I guess it would be -5/12, right? That's not real fun to graph, but I can kind of graph it. It's around here. Maybe I'll throw in something a little bit nicer. Maybe I'll throw in a 1 or a 2. Let's throw in a 2. And now I'm at 5 over -10, which is -0.5. Okay? Which, you could see, -5/12 is closer to 0 than -1/2, because that'd be -6/12. So by the time I get here, I am coming down a little bit. Maybe if I throw in 11, I'm at 5 over -1. I'm all the way down to -5. Okay? And I will tell you what's happening here. The curve gets closer and closer to this axis, and it gets closer and closer to that asymptote, right? And now you want to graph the rest of it. And so you'd have to try values where? Greater than 12. All right, so let me try 13. If I throw in 13, now I have 5, right? And that gives me probably enough information. If I'm at 13, 5 right here, I will tell you this is approximately what it does. Okay? Now, how do I know? Well, there are actually some other things that I need to check. So I know, for example, how do I know that this goes to the asymptote but never crosses it? We don't have the tools for that yet. Kind of got to wait a chapter or two, and then I'll show you how you can determine that kind of a thing. But at least this gives me an idea. What I'm really studying when I study 2.5 is I'm studying what is called by the book, and you guys may have seen this phrase, end behavior. Did you guys see that? It means what happens in the long run. And a lot of times that's what people really care about. We don't care what happens now. In the long, like play the stock market, right? If you're putting money in away to invest it, you don't care. Stock market's risky, right? If you're going to take it out next month, don't put it in stock market. Right? You may lose big time. But if you say, hey, I'm saving for retirement, over the long run, we have an idea what's going to happen. Okay? So that's what we're talking about when we talk about end behavior. All right, number 2. Oh, yeah, so what does this indicate? Oh, I guess I should finish with my final answers. I asked you guys to write statements like this. So what will we do as far as the vertical asymptote? I guess I could say limit as x approaches 12 from the negative side of 5 over x minus 12. What would that be? Yeah. How do you tell? Well, 2 ways. If you have a graph, I guess you can see it. If you don't have a graph, I suggest trying something a little bit to the left, and you see that when you throw an 11, you're at negative 5. And that gives you the idea that, oh, it's going negative. It's going towards negative infinity. So try something close to it on the left-hand side. Whereas when I tried something close to it on the right-hand side, I was positive. So it would be positive infinity on the other side. Does this make sense? Okay. All right, number 2. So f of 3 is non-zero over 0. So we have, well, a vertical asymptote where? Yep, x equals 3. So let me go over to 3 and draw my vertical asymptote. Does this function have any horizontal asymptotes? It does. Do you know where they are? Well, this is, yeah, go ahead.
Y equals 1.
It is y equals 1. How do you know?
Because
You've learned this before. What did you learn before?
you kind of ignore the plus 10 and minus 3, and then it's just x over x.
Yeah. So, see, notice the first situation, the degree of the denominator is larger than the numerator. Then you have y equals 0. But here, this is a different situation, you guys. We have the same degree. The same degree, top and bottom, numerator and denominator, right? If you have the same degree, my advice is going to be look at the leading coefficients. Do you know what I mean by the leading coefficients? That means the numbers in front of the highest degree term, which here, what are the coefficients of each of these polynomials? 1, right? So I'm going to tell you that the reason we got y equals 1 is because I do 1 over 1. Okay? Now you say you've learned it before. How do I know that works? Let me show you why it works. Okay? So again, when I say I'm going to do this with a calculus standpoint, and when I want to talk about a horizontal asymptote, what am I going to do? I'm going to do the limit as x approaches infinity of x plus 10 over x minus 3, right? So here's the trick now. The trick is divide the top and bottom by the highest degree term. In this case, it's just x. I want to divide by x on the top and bottom. So I'm not changing anything. I'm doing the same thing at the top and bottom. And what it becomes, this is your proof. I mean, you know, Duncan knows the asymptote is y equals 1. He's learned it. But here's the proof that verifies it. The limit as x approaches infinity of, okay, what do I get? Well, x divided by x is 1 plus 10 over x. And then here I get 1 minus 3 over x. So I'm taking the limit as x goes to infinity of this expression. Now take a look. 3 over x. What's going to happen to that when x gets really big? It goes to nothing, right? It doesn't matter. This approaches 0, and this approaches 0. So what I get is 1 plus 0 over 1 minus 0. I get 1. There's my proof that the limit exists. As long as you understand what happens to 1 over x, I have a proof. You guys follow? I think that's important. Because when you graph this on the graphing calculator, I could very easily see a student say, oh, the asymptote is 0. Because they just see it shrinking, shrinking, shrinking. But it's actually 1. I made this extra big so we could graph it, right? The same kind of thing. If I plug in a 0, I'm at negative 10 thirds. So I'm assuming your picture looks something like this, right? Where I am right here. Question? Reach you? No? Yep.
What if you flip like the numerator and denominator? Say it was like x minus 3 and then x plus 9, would that still be like a horizontal asymptote?
You would still have the same horizontal asymptote, but some things would change, right? So for example, if I did that, instead of my y-intercept being negative 10/3, I guess it would be negative 3/10, right? But it would be a very similar looking shape. There, you'd change some things about it, yeah. All right, number 3. We talked about this, right? You have what's called an indeterminate form. And so hopefully there's some algebra you can do. And there is, right? Right? So here, we can say that f of x is equal to x plus 5 times x minus 5 over x minus 5, right? And can I cancel? Well, I guess so, as long as I'm careful to understand that I know the domain of this function, right? I can say that f of x is just x plus 5, where x is not allowed to equal what? 5. That's kind of part of the domain. And so this particular problem, you don't have any horizontal or vertical asymptotes. As a matter of fact, if you graph it on a graphing calculator, it's going to be a line. So like, you know, the y-intercept is 5. Here's 0, 5. The slope is 1. So it looks like this. The only thing is, when you get to this point, there'd be a hole. Now, what point is that? It's 5, comma... Where is that hole? I guess it's 5, comma 10. How do you know? Yeah, you could plug in. It's interesting. If you plug in f of 5 here, you get an indeterminate form. But after you cancel, if you plug in f of 5, you get 5 plus 5 is 10. And that tells you where the hole is, in a sense. Okay? So I would say a couple things about this problem. Okay? I would say there are no asymptotes. I would say that f of 5 is undefined. But I would say the limit of as x approaches 5 of f of x equals what? 10. And this is the idea that we're trying to understand, is limits. And I talked about left-hand limits and right-hand limits. And are you approaching the same point? Yeah, that's important. Okay, otherwise the limit wouldn't exist. And this function is not continuous at x equals 5, because it's not defined there. Okay. All right, number 4. So for number 4, let's see what we have. Well, I guess to start, you guys know that I have a vertical asymptote where at x equals, I guess I have to solve 3x minus 2 is 0, right? So I get x is 2/3. So here's number 4. So maybe I start with that. Okay? And I'm going to say next, no horizontal asymptote. Why? Well, degree of numerator is larger. So if the degree of the numerator is larger, there will be no horizontal asymptote. Okay? So as a matter of fact, you could say the limit as x approaches infinity of 9x squared minus 25 over 3x minus 2 is, you could say, infinity. It grows without bound, as we're going to see. Farther to the right you go, the bigger it gets. Here, throw 1,000 in. Let's find f of 1,000. Because what's 1,000 squared? Oh, you guys don't know that? 3 zeros become 6 zeros. So what's 1,000 squared?
1 million.
1 million, right? So what is this? This is 9 million divided by about 3,000. This is about 9 million, right? I mean, it's huge. It's not approaching anything at that point. Okay? So if the degree of the denominator is larger, if the degree of the numerator is larger, you don't get any horizontal asymptotes. Now it turns out there is an asymptote you can get besides the vertical one. It's called oblique asymptote or a slant asymptote. How many have seen this? It's in the book for today's reading. I can show you a picture. Okay? And I can show you how to find it also. All right? So let's go ahead and do that maybe. Okay? So yeah, let's talk about an oblique asymptote. We get, it's also called a slant asymptote if you want. We get by dividing. So all I have to do is realize that that fraction bar means divide. And so what I need to do is I need to take 9x squared minus 25 divided by 3x minus 2. Have you guys done this? Polynomial long division? I think we did it once in this class, right? Sometimes what I think helps is this. I'll write plus 0x here, just to kind of hold a place value, if you want. And I'll say, okay, what times 3x would give me 9x squared? 3x. And then I do 3x times the 3x minus 2, and I get 9x squared minus 6x. Okay? And now, when I draw my line, I change my signs because I want to add. I'd rather add than subtract. So I'll just change the signs, then I can add. I get 6x minus 25 is my remainder. Okay? And now I say, what times 3x would give me 6x? 2. So I'll write plus 2 here. And 2 times 3x minus 2 is 6x minus 4. When I draw my line, I change my signs. Negative 25 plus 4 is negative 21. Now, what is it that I just did? I just showed you, using long division, another way to write the function. We can write that 9x squared minus 25 over 3x minus 2 is actually equal to 3x plus 2 minus 21 over, remember how you used to do this when you had the leftover remainder? You'd say 21 and 2/3, right? Or this would be minus 21 over 3x minus 2. See that? And so now I can say what happens when limit, so this piece will go to 0 as x goes to infinity. This piece goes to 0. And so in the long run, the function is basically going to look like 3x plus 2 in the long run. That's a line. So what I could do is I could graph x equals 2/3. All right, so let me graph that. Here's, let's say, here's 1, here's 2. So x equals 2/3 would be, I'll put it right here. And then I could graph y equals, so this is x equals 2/3. I could graph y equals 3x plus 2. So I'll go here to this y-intercept, have a slope of 3. Okay? And that's a slant asymptote. And so now if I want to sketch a graph of the function, well, I can do the same thing. I can, for example, find f of 0. That's 25 halves, which is 12.5. That's way up here, I guess. Okay? But I guess the point is that as I move negative, what's going to happen is it's going to get closer and closer to this line. And then I have an asymptote up here. Okay? And the rest of the curve is going to look kind of like this. Do you guys have questions on that? So I believe it was example 3 in your book had another picture of that. And so I want to show you, my picture's only so good. I want to show you another picture that maybe shows it a little better. So this is under end behavior. Yeah, so first of all, this example 3 is really nice for demonstrating the rules we have. Part A, what's our asymptote? Take a look. Can you identify it quickly? Horizontal asymptote where for part A? For part A, it would be y equals 0. How do I know? Degree in the denominator is we have x squared in the denominator, only x in the numerator. How about B? What's the horizontal, what's the end behavior for part B? Horizontal asymptote at y equals 4, because you do 40 over 10. Those are the same degree. Part C, I'd say that the end behavior, this thing goes to infinity. And part C does not have a slant asymptote. You could try the same dividing trick, but you wouldn't get a line. You need the degree to be exactly 1 bigger to do that dividing trick. Here we go. Example 4 does it. So let's show that. Yeah, this big box doesn't mean much to you, I don't think. But let's see. Does that do it? No. Solution. There we go. So they do the same dividing trick that I did. They divide top and bottom by x, right? Oh, they did it a little differently. They didn't do the long division. Interesting. Here they did. Using long division, yeah, they don't even show it. They rewrite it like this. So you have y equals 2x plus 4. That's funny, they don't even show it. Well, I'm glad I showed it then. But I wanted to show you the picture of their, here's the slant asymptote, 2x plus 4. And here is the vertical asymptote for this one would be x equals -1. And again, you can see what the function looks like. So that's another example. You guys got that? Okay. This is such an important idea that I'm going to record this just on the little recording for you guys. Yeah, example 5. Determine the end behavior of this function. Solution. Oh, well, there it is. They say, look, do some work here, and instead of, so yeah, you divide top and bottom, and they kind of show their work there, but I guess the point I want to make is all the work up above shows 2 different limits. As x goes to infinity, this function, which crosses both asymptotes, then comes back to 2. But when x goes to -infinity, here, let me move x over here, it's going to cross, and then it's going to start growing again. And eventually, -2 is the limit. It's a great function. But I guess probably what happens is, the algebra teacher wants to teach you asymptotes. They do some very basic examples. They won't touch this one, right? And so then you might not know what's going on exactly, that it can cross